Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to discuss about RISC-V processor architecture, and we are going to discuss what are the different kind of blocks we are going to have and we are going to build in our particular project series. Now, we are in this particular session, we are going to discuss about the top level block diagram and memory subsystems and pipeline stages and support units. So first, let's try to understand about top level block diagram. So first of all, we are going to have an AXI interconnect at my top, and using this AXI interconnect, I'm going to connect via the memory, where I'm going to have the memory dedicated for my instructions, as well as memory which is dedicated separately for data. So from that, I'm going to get those particular memory contents into my instruction cache as well as data cache. So basically, this instruction cache is going to fetch the instructions from your main memory, which is going to store the instructions via the EXA interconnect, and your data cache is going to fetch the instructions or the data from your main data memory, and it is going to store it. Now we are going to have different stages, and first stage is instruction fetch unit. So first of all, we are going to fetch an instructions from instruction cache. And if you don't know about what do you mean by instruction, what do you mean by cache, what do you mean by instruction cache and all, and what is the format of instruction and all, no worries, we are going to discuss them in great detail. Now, after instruction fetch, we are going to pass it to something known as instruction decode, where we are going to decode what is the instruction which is present. And whatever the decoded instruction, let's say suppose if it's a register instruction, then I'm going to take the contents from a register file, and I'm going to forward it to something known as execute unit. So the instruction will be executed over here, and I'm going to have something known as hazard or my forwarding unit. Now, what do you mean by hazard unit? That we are going to discuss in few seconds. Next, from this execute unit we are going to memory unit, where we are going to deal with memory related stuff, and next is write back unit. So these are the different kind of modules we are going to implement in our RISC-V processor. Now, so the first, let's discuss about memory subsystem, where I'm going to have the first one is AXA interconnect. So AXA interconnect we are going to use, where we are going to store the data inside my instruction cache and as well as data cache at the same time parallelly. So this is a top level bus implementing the AMBA AXA protocol, where separate read and write address and the data channels with valid or ready handshaking. Okay. And it is going to arbite and route request between instruction side as well as data side caches and the outside world, where main memory and peripherals. So I'm going to have different memories, two separate memories for my particular data as well as instruction, and from that my AXA interconnect is going to fetch those, and it is going to store inside my instruction cache as well as data cache. And the single point of contact between the processor code and the single point of contact between the processor core and everything of the chip is done using this AXA interconnect. And let's say suppose if I want to connect a peripheral, let's say suppose a UART controller or an SPA controller, then I'm going to use this particular same AXA interconnect, and I'm going to connect them using my AXA interconnect. Next is instruction cache. So basically, it is going to catch recently fetched instructions. So instruction fetch unit doesn't need external memory on every fetch. Let's say suppose if I want to fetch a particular instruction, and instead of depending upon the main memory, I'm going to use this instruction cache and my instruction fetch unit, which we have seen previously, that it is going to fetch the instructions from something known as instruction cache. And we are going to return the instructions directly to the instruction fit on a hit. Okay, so this is how we are going to use our instruction cache. Now we are also going to have something known as data cache that I have shown you already, where it is going to caches load or store data, so memory doesn't need external memory on every axis. So this memory model which we are going to develop, instead of directly communicating with the main memory, we can basically store that particular data inside something known as data cache, and we can fetch or we can store it inside this particular data cache. And we have something known as instruction fetch unit, where this particular instruction fetch unit is going to hold something known as program counter. Now, what do you mean by program counter? What is the importance of it? And all we are going to discuss in great detail in the upcoming sessions. where if I want to briefly explain about you the program counter, basically this instruction fetch, it is going to store the program counter. Program counter is kind of a pointer towards the instructions, and this instruction fetch unit is going to have the logic for the program, and it is going to request the instructions at current program counter from instruction cache every cycle, and it is going to compute PC is equal to PC plus 4. Next is instruction decode unit. Whatever the instruction fetch unit has fetched from the instruction cache, it is going to forward to my instruction decode unit, and instruction decode unit is going to decode whatever the instruction was. Okay, and if you don't know what do you mean by instruction and what is the fields which are present inside our RISC-V instructions and all, we are going to discuss in great detail. Just now, I'm basically showing you the process of how the things are going to work, right? Next is execute unit, where it is going to execute the instruction. So whatever the instruction unit has decoded, those particular things will be executed with something known as execute unit. So it is going to it is basically houses the ALU and branch comparator or target address, and it is going to perform the arithmetic or logical operations or computes the branch outcomes and target address. So this is what my execute unit is going to do. And next is something known as memory access. So this is the module which performs the actual loads and stores again the data cache for load or store operations. And for non-memory instructions, the ALU result simply passes through the unchanged. And it results can be forwarded back to execute unit or instruction decode unit via the hazard or forwarding unit depending upon the instructions. Now, in which cases those particular instructions are forwarded with the hazard unit and all, we are going to discuss in great detail. And we have something known as a write back unit, where the final pipeline stage, this is the final pipeline stage where we are going to write down our result into the destination register, and it is going to complete the instruction lifecycle through the pipeline. So these are the different modules which we are going to use for basically achieving my pipelining. Okay, now what do you mean by pipelining? Let us try to understand in great detail. For example, let's say if I'm going to have, so in my pipelining, I'm going to have something known as instruction fetch, instruction decode, execute, memory, and write. Right. So let me write down over here. So I have something known as instruction fetch and instruction decode, and I'm going to have after instruction decode, execute, memory, and write back. Execute, memory, and I'm going to have something known as write back. Let's say I have three instructions: instruction one, and instruction 2 and instruction 3. Let's say suppose if this instruction 1 has been fetched from the instruction cache, and let me write down over here instruction 1, and this is my cycle 1. In cycle 1, instruction 1 was fetched, and in cycle 2 what I'm going to have is, in cycle 2 I'm going to decode my instruction number 1, and at the same time I'm also going to fetch my instruction number 2. So instruction number 2 will be fetched. So I'm going to write down here if, and in cycle number 3 instruction 1 will be executed. So inst1 is basically executed, and at the same time instruction 2 will be decoded, and instruction 3 will be fetched. So at the same time, multiple operations are going to happen. And for this multiple operations to complete, we are going to have this modules working parallelly. Okay. Now, let's try to understand about something known as hazard or forwarding unit. And in great detail, we are going to discuss how these modules are basically helping us to basically perform this pipelining and all. Now, let's try to understand about hazard or forwarding unit. So basically, it is going to monitor instructions in execute, memory, and write back to detect data hazards. And it is going to forward results directly from execute or memory output back to execute's input where possible, avoiding pipeline stalls. Okay. So let's try to understand what exactly it is doing. So let's try to understand first of all what do you mean by an hazard. Basically, a hazard is a condition that prevents an instruction from executing in its intended clock cycle with a pipelined processor. For example, if I'm going to have multiple instructions executing simultaneously in different pipelining stages like instruction fetch, decode, execute, memory, and write back. Normally, one instruction completes every cycle after the pipeline is filled. However, we might get some kind of situations where one instruction interferes with another. and these situations are called as pipeline hazards. Let us try to understand this in great detail. For example, so what is going to happen if these hazards are not handled correctly? Then we might get incorrect results, or we might execute wrong instructions, or we might also lose data, and the overall performance will be reduced. And for avoiding these problems, we are going to use something known as hazard detection unit and a forwarding unit. Now, what do you mean by an hazard and why these hazards are occurring? Let us try to understand. This is the example which I have explained you previously. Let's try to understand this example again. These are my cycles. So this is cycle number one, two, three, four. In cycle number one, let's say I have instruction one. So basically, I have four instructions to be executed: instruction one, instruction two, instruction three, and instruction four. Now, let's say if I have first instruction to be fetched in the cycle number one, first instruction is fetched. Now, in the second cycle, I'm going to decode whatever the instruction was fetched. And at the same time, I'm also going to fetch one more instruction to the second instruction. Okay. Now, at the third time, I mean, in the third cycle, I'm going to execute the first instruction as well as I'm going to decode the second instruction, and I'm basically fetching the third instruction. This process we have seen on the screen, right? This is known as pipelining. And here, multiple instructions are executing simultaneously, if you are able to see it, right? Now sometimes what happens is, uh, they complete for hardware, they are going to compete for hardware resources or depend on each other results. So if multiple instructions are executing parallelly, sometimes what happens is they are going to compete for the hardware, and that is where you are expecting hazards. Now, what are the different kind of hazards we do have? Is one is structural hazard, and another is data hazard, and followed by control hazard. Now, first of all, let us try to understand what do you mean by structural hazard. So, for example, let's say if I'm going to have an instruction, which is instruction one basically says load word, register, and 0 and x1. Okay, so this is an instruction where it requires memory during memory stage. Okay, so because it's a memory instruction, LW basically stands for memory instruction, and we will discuss in great detail how to analyze an instruction, what do you mean by this instruction and that instruction and all. Now, let's say this particular instruction is required a memory, okay, because it's a memory instruction. Now, at the same time, we do have an instruction two, and don't think that we are going to complete first instruction one and we are going to instruction two. No, first both the instructions may work together, because you can see over here, instruction one and instruction two are getting executed at the same time. Okay, because in pipelining we might get like this. Now, what is going to happen? Instruction 2 is an addition operation where we are going to add the contents of x7 and x8, we are going to store in x6. So this requires the same memory during the instruction fetch stage, cycle number 4. So what is that? This particular instruction, if you carefully observe, in the IF stage, we are going to, let's say this is my second instruction. And here in the second phase, I'm going to have this particular conflict. So what is the conflict? Let's say suppose if I have only one memory, if I have only one memory where both data as well as instructions are stored. So I'm going to have a common memory where data and instructions are stored. If I'm going to use this LW, which is having a dependency upon the memory, and it is depending upon this memory, where instruction 1 is depending upon the memory. Now, my second instruction is also depending, my second instruction in the instruction fetch stage, I need to fetch an instruction, right? The second instruction. This is also depending upon the memory. So both the instructions are now depending upon the memory. This is nothing but the conflict, and this is nothing but my structural hazard. And in modern processors, we are not going to get this kind of structural hazard, because our in our modern processors and whatever the project which we are now going to do is going to have separate memories for data as well as my instruction. So that's the reason I'm not going to get this hazard. Okay. Now, yeah, that is what written over here. So modern RISC-V processors eliminate the structural hazard by providing separate hardware resources. Examples: separate instruction memory, separate data memory, instruction cache, and data cache. Now, next is data hazard. Now, let us try to understand what do you mean by a particular data hazard. So basically, data hazard occurs when an instruction depends upon the results of a previous instruction that has not yet completed. For example, if I have two instructions add x5, x1, x2. This is instruction number 1 and this is instruction 2. And instruction 1, if you carefully observe, I'm going to add the contents of x1 and x2 and I'm going to store it in my x5. And in the instruction number 2 is adding the contents of x5, I mean subtracting the contents of x5 and x3, and it is storing the results into x6. Now, instruction 1 produces x5 and instruction 2 immediately needs x5. Okay, if you carefully correlate this particular instruction with this example of pipelining, let's say I'm going to have add x5, x1, x2 and subtract x6, x5, x2 like this, let's say. Now, this is my instruction number 1 and this is my instruction number 2. Now, what is going to happen? Instruction 1 is being fetched from the memory. Okay, fine. And instruction 1 will be decoded. Okay, it is decoded only. Decoding, if you want to perform this operation, it will be done in your execution stage. Decoding is different and execution stage is different. Decoding, in the sense, you're basically trying to understand what instruction is trying to tell you. And if you want to perform the addition operation or if you want to perform the subtraction operation, that particular operation will be done in your execution stage. So in this particular stage, the operation will be performed. Let me show you quickly. Yes, in the execution stage, your operation will be performed. Now we are in still in decode stage where actually the instruction is, we are basically trying to understand what instruction is trying to tell us. Okay. Now, where are we coming to? This one. Yeah. Now, what is happening in the second cycle? We are trying to decode what exactly the instruction 1 is telling. So we are decoding this instruction and at the same time, we are fetching this instruction from the memory. Okay. So decoding is happening and fetching is happening. Now, in the cycle 3, what is happening? The cycle 3, if you observe, we are executing this particular instruction where we are going to execute this particular instruction x5, x1, x2. And the second instruction we are decoding. We are trying to understand what is happening in this particular instruction. Okay. So this is in the same cycle we are trying to decode what exactly this instruction is trying to tell us. Now, in the fourth cycle, we are going to store it into the memory. Okay, this particular operation is completed in the third cycle. Addition operation has been completed and the result will be stored inside your memory or into the register, and at the same time my second instruction is expecting the content of this particular x5. So here the race condition is going to happen because into the register file, because it's a register operation, right? Into the register file, one particular instruction is trying to store and another instruction is parallelly trying to copy it. So here you might get the previous value which is present inside your register. This is what we are going to have in the case of my hazard. Okay, so that is what it is written over here. Now, what is that we are going to do in the if we are going to have this particular data hazard? Then we are going to use something known as forwarding or bypassing. So instead of waiting for the write back stage, the processor forwards the ALU result directly into the next instruction. So instead of writing back into the register or the memory, we are going to directly give it to the next instruction. So this is what we are going to deal in the case of my data hazard. And control hazard we will discuss in our next sessions. Now, next is our control unit. So basically this control unit is a unit which is going to generate control signals from the decoded opcode. And like for example, after decoding, I came to know that it's an ALU operation or it's a memory operation or it's a register write enable operation. Who is going to tell us? A control unit is going to tell us after decoding the instruction, and it is going to receive the decoded instructions from the instruction decoder. Instruction decoder, it is going to give it to the control unit, and control unit is going to control, or it is going to decide what type of operation it should do, whether to execute or whether to memory, whether to show it in the memory or whether to write back. Okay, so this is what the control unit is going to do. So if I want to check out the overall data flow, first of all, I'm going to get the instruction memory or instructions or the data from AXA, and next I'm going to fetch it, and next I'm going to decode it, and next I'm going to execute and memory and write back into the register file. So my hazard or forwarding unit and the control unit run alongside the pipeline rather than sitting in line with it. So this is what the entire flow of RISC-V pipeline architecture, and we are going to implement it using Verilog from our next session. Yes, so if you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.